Hello, everyone. My name is Hugo Dorado. I'm a researcher from the Biodiversity Seattle Alliance, and today we're going to talk about two different supervised learning models. One of them is called random forest, and the other one is regression trees, also known as CART. In English, means classification and regression trees. This material is part of the um, part related to data mining agriculture developed by Biodiversity SEAT, Illinois CIMMYT, and the CCAPS project. Beginning with the CART. This algorithm has special characteristics that make it very popular among the different models that exist for supervised models. One of them is that this algorithm is flexible for typical data. Most of the models are restricted to use information with missing data and requires previous process in order to execute it. For the CART, this is not a restriction, so we can use data sets where there's some missing information. Apart from this, we're also going to see that these are very easy to interpret. They can be visualized in a structure of decision rules, so it facilitates the discussion of results. And different to other models, this also allows to visualize the interactions that can occur between variables. And there are two types of trees. The classification trees for qualitative outputs and the regression trees for quantitative output variables. This is an example of the construction of a decision tree where we are deciding we should accept a new job offer. To take this decision, the first thing that we should do is to assess if the conditions are favorable for us to take a positive decision. The first thing that we'll assess is the most important thing for us. In this case, it could be the value of the salary. If our salary, for example, is below our current salary, we could take an immediate decision on declining the offer. Instead, if we have an offer that's above our current wage, we'd probably begin assessing other conditions before taking a definitive decision. One of them could be if we are willing to commute for more than an hour every day to reach that working place. So, based on this, we could decline the offer because the commute time every week would be very long, or we can continue assessing other characteristics that could also be of our interest. For example, if the job offers free coffee or not. This would be less a characteristic with less importance, but some people who are in love with coffee, it could be something that has a lot of weight for them in order to take a decision and accept a job or not. So this is how these trees can be interpreted for classification and regression. For the revision that we're going to perform about the cards, and also in Random Forest, I've used this information from the Simply Learn platform that you can find in SlideShare. This is the link, and there's a lot of material available to understand how these models work. So if you have any time, you can go over this material. It's going to be very interesting. In this slide, we can see the different components of a cart. Among them, we can see different nodes, and most of these nodes come with ramifications. Every node divides the data set in two parts, as we can see here. In this case, we begin with the initial data set, and based on a decision, we divided the data set in two. And we have more variability here as we start to divide the data set in two times at a time. We can observe that that variability starts to reduce until we are able to find result where the variability is minimum. Among those components in each one of the nodes, we can identify the root node, that would be the first node, where the variable that's most important is going to be assessed to divide the data set. And from there on, there are mode nodes dividing, which are decision nodes. And the last two have no more decisions, and these are called leaf nodes or terminal nodes. To create those divisions between each one of the nodes, we need a criterion that's known as entropy. This entropy allows us to assess the uncertainty in each one of the nodes, so the data set that is contained there. So in the initial nodes, we'll obviously find a higher entropy since there's a higher variability. And as we start to build our tree and we create more partitions, then that entropy starts to dissolve. And there's also another criterion called information gain, which allows us to compare the uncertainty that you have based on the creation of more and more nodes. So basically, that's the difference of the current entropy that can be perceived in the nodes based on the entropy of the last node. And this helps us to decide sometimes until when you have to make the tree grow. And here we can see how the tree construction occurs in a very simple way. In this case, we have a set of fruits that we'd like to classify. We would like to create a model that if we have a new fruit, we'd be able to define if it's an apple, a grape, or a lemon. So in a database, we would have associated the variables of those fruits. In this case, it would be the diameter or the color. So in the construction of our tree, we could identify that the most important thing that helps us to classify this immediately, or at least a fruit, would be the diameter. The diameter would help us to separate the grapes on one side and the rest of the fruits in another side. So by doing this, we've already reduced the uncertainty and the entropy in our second nodes. And the next characteristic that we could assess in order to have a perfect division in our classification tree would be the color. So if the color is yellow, we would be able to identify that these are lemons. And if it's false, then by default, they would be apples. We can also see in these trees that in the last parts of the tree, in the terminal nodes where there are no more ramifications, the entropy would be 0. We would have no uncertainty because we only have one class among the difference that we could assess. So in each terminal node, we could wait, especially with the tree that we built, that the entropy will be reduced to 0. To execute regression trees in R, we have this rpart function that is part of the package called rpart. So there we can calibrate 4 different parameters for building these trees. Among them, we have this one that's called min-split. That's the minimum number of observations in a node for it to be split. By default, it has a value of 20. So what this tells us is that in the construction of the tree, the function will verify and make sure that at least in that node that's being created, there should be more than 20 observations before continuing generating new ramifications. So one of the first criterions that are taken into account is this. The second one would be min bucket. That's the minimum number of observations in any terminal node or leaf node, which are the ones that are in the end. So this is estimated based on the number that we've identified here, the min-split divided by 3. This is used to stop. Otherwise, the tree can continue growing until there are very few observations. Another parameter that can be used, and this is the most common one, is the CP. That's the complexity parameter, which assesses the impurity criterion when creating a new partition. So that criterion could be the index for information gains, and by default it has a value of 0.01. What this means is that if there's a partition that has no more information in relative terms, then the tree will stop growing until that point. And finally, there's this function called max depth that also limits the possible amount of nodes that can be created. By default, it has 30. So the maximum depth of the tree would be this value that we condition. We can configure these parameters however we want, and what we can do if we want to use any of these parameters, we can perform experiments with different values. They could be close to the ones that we have here by default, and then we'll assess them based on a test data set to see which one performs the best for our model. This is the example of a card for the yield of irrigated rice in Nicaragua. The response unit was in quintals, and we had predictors related to the climate. There's one for population here. So what we wanted to do is to see the relation between the different variables so that we could identify what was the best possible scenario for producing the highest yield. And we did this with CAPS. So we can see that in the first node, in the root node, we have 100% of the data. The average was 95 quintals. And the first variable that we use to divide this data set would be accumulated sunlight. It could be divided in the half between 43 and 57%. So there was already a difference of 9 quintals, supposing that these are the most productive ones. So the interesting thing about these caps is that it allows us to assess the interactions in the data sets. And after dividing the values of solar energy that was accumulated in the last phase, the route shows that the variables could have a different behavior in each one of those divisions of those branches that we created. So in that case, we were interested in knowing what was the one that had the best yield. So we concentrated on the terminal nodes between the bluest are the ones with the highest yield. This would be the case of an average yield of 109 quintals. And the optimal conditions were for the sunlight during the filling phase would be equal to 16,000 calories on 16 cubic centimeters, and the solar phase in the vegetable stage should be below 21,000 calories on every cubic centimeter, and the final population should be above 200 plants per a certain area. So these are the most favorable conditions for rice yield. We could also identify what were the ones the least favorable. That would be this path. So as you can see, the classification and regression trees have a high potential for finding patterns on databases that can be easily read and interpreted. So, and this information can be discussed with other experts with a simple explanation. From this moment, decisions can be taken to have the best favorable conditions for climate and also for the control of the population or the density of the plantation.